Hello, chemistry students. Here are your Chapter 14, Day 3 notes. We're starting at Section 2, Periodic Trends, and we're going to go through and finish the ions section. Excuse me. So, Section 2, Periodic Trends, we're going to start by talking about our trends in our atomic size, or the size of our atoms. And how is it that scientists measure this? Okay. This is measured when chemists look at the units that form when atoms of the same element are joined to one another. These units are called molecules. So what we're talking about is having an atom of fluorine bonded to another atom of fluorine. That's how scientists have been able to study the size of these atoms. Specifically, they use the distance between the nuclei, which is just the plural of the word nucleus, of the atoms to estimate the size of the atoms. The definition of the atomic radius is half of the distance between the nuclei of two atoms of the same element when the atoms are joined. Now, obviously, when we're talking about an atom that we can't even see, and now we're talking about half the size of that atom as a radius, these are very small. So they're often measured in picometers, which are abbreviated PM. And in general, atomic size increases from top to bottom within a group and decreases from left to right. Across a period. And we already explored this on our ChemQuest 21 Trends in Size. So the group trends, remember these are the columns on the periodic table. And to kind of talk about the group trend, we'll take a look at lithium and sodium, and we'll draw those Bohr diagrams like we did on our ChemQuest. So lithium has 3 protons in its nucleus. So it has 2 electrons in its first energy level and 1 electron in its second. This is lithium. We're going to look at sodium. Sodium has 11 protons in its nucleus. So it has 11 electrons, 2 in its first, 8 in its second, and that leaves 1 electron in the third. So this is sodium. So remember, as we kind of looked at group trends, one of the things that we look at was the pull of the nucleus for those electrons. And in the first energy level, the pull of the nucleus for these electrons is a +3 pull. But when we move into our second energy level, remember that pull becomes +1 because of the shielding of the electrons in the inner energy levels. So those inner electrons are canceling out or shielding some of that positive charge from the nucleus. And because the first energy level in lithium has 2 electrons in it, the shielding is 2. So the +3 charge is reduced by 2, leaving that electron in that highest occupied energy level to feel a pull from the nucleus of +1. When we look at sodium, again, our first energy level, that pull is +11 because there is no shielding occurring. When we get into the second energy level, we have shielding of the first energy level, which contains 2 electrons. So that's a shielding effect of 2. And so the electrons in that second energy level are feeling a pull of +9 from the nucleus of that atom. When we get to our third energy level, we have 2 electrons shielding in the first energy level. We have 8 electrons shielding in the second energy level, totaling 10 electrons, which means we're reducing that pull of +11 by 10, which leaves us a pull of +1. So remember, one of the things that we noticed about the pull from the nucleus was that the nuclear pull on the electrons in that highest occupied energy level is the same for all elements in the same group or family. So we have the same charge acting in both of these elements. So that's not affecting the size of these atoms. So remember, we said that this group trend is that there's an increase as we go from top to bottom. The reason for that increase here is because we are adding energy levels. In our lithium, we only have 2 energy levels. In sodium, we have 3 energy levels full of electrons. And so that is the reason why we see the increase in atomic size from top to bottom within a column or group or family of the periodic table. It's because we're adding an energy level each time we move down the group. Which is making the atoms larger. In terms of our period trends, again, we're going to look at 3 elements on the periodic table. So we will look at sodium again. Well, actually, let's do magnesium. So that has a pull of plus 12. So 2 electrons, 8. And that leaves us 2 electrons in our third energy level for magnesium. If we look at silicon with plus 14, and we have 2 electrons in our first energy level, we're going to have 8 additional ones in our second. And then we're going to have a total of 4 more out in our third energy level for silicon. And if we take a look at chlorine, which has 17 protons, 2 in our first, 8 in our second, which leaves us 7 in our third. Right, so again, we want to kind of look at the same things we looked at with our group trend. We want to look at what is the pull that the electrons feel in each energy level from the nucleus. In our first energy level for magnesium, we feel a plus 12 because there's no shielding. In our second energy level, we have a shielding of 2, so we're going to feel a plus 10. And lastly, in our third energy level, we have 10 electrons total shielding. And so we have a pull of plus 2 with 10 electrons total shielding. When we take a look at silicon, again, our first energy level is going to feel a plus 14 because there's no shielding. In our second energy level, we have 2 electrons shielding, so we're going to feel a plus 12. And when we get to our third energy level, we're going to feel a plus 4 because, again, we have 10 electrons total doing our shielding from our first and our second energy level, meaning we're going to cancel out 10 of that positive 14 pull. When we look at chlorine, again, our first energy level is going to feel that plus 17 because there's no shielding. In our second energy level, we have a shielding effect of 2, so we're going to feel a plus 15 pull for those electrons in that second energy level. And in our third energy level, we're going to feel a pull of plus 7 because, again, we have 10 electrons in our total completing our shielding in our first and second energy levels in chlorine. So notice what is staying the same in all of the elements in this period is the shielding. That does not change. We have 10 electrons shielding in all of these. What is changing is the pull from the nucleus. Magnesium is only having a pull of plus 2. Silicon has a pull of plus 4. And chlorine has a pull of plus 7. Remember that a stronger pull means that the electrons are being pulled more tightly toward the nucleus. Therefore, the atom is smaller in size, which means, okay, chlorine is our small atom and magnesium is our, oops, sorry about that, large atom. And so our size decreases as we go from left to right across a period. So as we get ready to talk about chemical bonds and whether compounds and elements are going to form an ionic or a covalent bond, we're going to talk for the first time really specifically about ions. Now, we've mentioned them before. I told you that it was really careful back in chapter 5 that we refer to our atoms as atoms, because by calling it an atom, that means that it has an equal number of protons and electrons. By contrast, then, what is an ion? An ion is defined as an atom or group of atoms that has a positive or negative charge. Now, remember, when we're not referring to an atom as an ion, when we call it specifically an atom is electrically neutral because it has an equal number of positively charged protons and negatively charged electrons. So remember when we talk, for example, about a sodium atom, we're talking about sodium, which has an atomic number of 11, so it has 11 protons and 11 electrons. Now, technically, when we're talking about forming an ion, we could gain or lose protons, electrons, or neutrons to form an ion. Which is it? And why? So what I'm asking you to consider right now, and I want you to think about, is we know that inside an atom we have protons. We know that inside an atom we have electrons. And we know that inside an atom we have neutrons. So to form an ion, okay, we could gain or lose protons. We could gain or lose electrons. We could gain or lose neutrons. All three of those particles are inside of an atom. So which one is it that we gain or lose, and why? So I want you to think about that for a couple minutes and really kind of come up with a reason why and what you think it is before you continue to listen to the video. So let's start First with neutrons. Remember that neutrons have no charge. So would gaining or losing neutrons have any effect on forming an ion, making this atom have a positive or negative charge? No. So therefore, we are not going to gain or lose neutrons. And you probably should have realized that because we actually have already talked about what we call atoms that have different numbers of neutrons. What we call atoms that have either lost or gained neutrons. Remember, those are called isotopes. Right? Isotopes were atoms of the same element that had different numbers of neutrons. So there's kind of a couple reasons that we're not going to be talking about gaining or losing neutrons. Number one, they don't have a charge, so it wouldn't accomplish what we want to accomplish. Number two, when we have different numbers of neutrons in atoms, those are isotopes. They're not ions. All right, let's talk about protons. Protons have a positive charge. So we could gain protons and get a positive charge. We could lose protons and get a negative charge, right? However, I need you to remember what makes helium-helium. What makes carbon-carbon? What makes polonium-polonium? Remember that protons, okay, are equal to the atomic number. And the atomic number is different for every element on the periodic table. So we could change the number of protons. The problem with that is if I have 5 protons, I'm boron. And if an element has 6 protons, it's carbon. It's not the same element. So this is not going to work. It's not happening to form ions because it changes what atom we have. And we're not trying to change that. We want to take an ion is going to be the same atom, but it's going to have a positive or negative charge. So we've just said we can't lose or gain neutrons. That's what we do when we have isotopes. We can't lose or gain protons because that would change what atom we have. So that leaves us with electrons. Now, electrons, remember, have a negative charge. Okay, and this is what we're going to do. We're going to change our number of electrons. So change number of electrons to form ions. And it's our only choice because neutrons won't give us a charge, plus those are what isotopes are. Protons would give us a charge, but changing the number of protons changes the atom altogether. So our only option as we start to talk about forming these ions is that we're going to have to talk about gaining or losing electrons. So positive and negative ions form when electrons are transferred between atoms. So again, transfer means that we're going to have an atom that's going to give up an electron, and we're going to have an atom that's going to gain an electron. Specifically, the atoms of the metals tend to form ions by losing one or more electrons from that highest occupied energy level. So we're always going to be talking about gaining and losing electrons that are on the outside edge of that atom. Right? We're not like reaching in and grabbing an electron from the first energy level that's way buried inside that atom. We're talking about always pulling electrons, removing electrons, adding electrons to that highest occupied energy level. Now the metals, remember, that's the left side of the periodic table, and below that heavy stair-step line. Metals typically are going to form these ions when they give up or they lose one or more electrons from their highest occupied energy levels. We call this forming a cation or a cation. A cation is an ion with a positive charge. This charge, okay, is written as a number followed by a positive sign. Now, I'm not real picky about that, so I don't care if you write it 2 plus or plus 2. These are written as a superscript, so that means that they're up high and after the symbol. And in a cation, we have lost electrons. Therefore, we're going to have more protons than electrons. Therefore, we have a positive charge. To look at an example, we're going to look at a sodium atom versus a sodium ion. So sodium atom is Na, and when we look up sodium on our periodic table, it has 11 protons and 11 electrons. Sodium ion is Na with a +1 charge. It's still sodium, so it has to have 11 protons. But what this +1 charge is telling me is that it has one more proton than it does electron, which means it's lost an electron and it has 10 electrons. Now, in a little preview for what's to come, who else on the periodic table has 10 electrons? Neon. Remember a while ago I told you that the noble gases are the cool kids on the periodic table? And when every other element forms a bond or forms ions, they're going to do so in an effort to be like the noble gases. What sodium has done by becoming a sodium ion is have the same number of electrons as neon. That's not a quinky dink. So these were the atoms of the metals that tend to do this, and they form these cations. Right? The atoms of the nonmetals tend to form ions by gaining one or more electrons. So remember, our nonmetals are to the right and above that heavy stair-step line on our periodic table. When an atom gains one or more electrons, it becomes called an anion. An anion is defined as an ion with a negative charge. This negative charge is written as a number followed by a negative sign as a superscript. After the symbol. In an anion, we gain electrons. Therefore, we have more electrons than protons. Therefore, we have a positive charge. To look at an example, again, we're going to look at a chlorine atom versus a chlorine ion. Chlorine atom, chlorine is atomic number 17, so a chlorine atom has 17 protons and 17 electrons. When chlorine becomes an ion, it still has to have 17 protons. Because remember, if I changed the number of protons, I wouldn't be chlorine anymore. But now, chlorine as an ion has a -1 charge, which means it has one more negatively charged electron than it does positively charged protons. So it's gained 1 electron, so it has 18 electrons. Now, again, in that little preview of what's to come, who else on the periodic table has 18 electrons? Argon. And again, told you before, we're going to talk about it more and more. The noble gases, group 8A or 18, they're sort of like the cool kids on the periodic table. They don't get involved in forming chemical bonds. They don't form compounds typically. They do that because they're really stable the way they are. So every other element on the periodic table, when it becomes an ion, when it gets involved in bonding, it's doing so that it can feel like it's a noble gas. And chlorine becoming an ion and getting that -1 charge, it feels like it's a noble gas because now it has 18 electrons just like its neighbor argon, the noble gas. So that brings us to where we are going to stop for today. Have a great day. I will talk with you tomorrow.